All right. Good morning, everybody. Welcome back. Uh, so for today, let's start a new chapter, and we will probably work today and Monday in this chapter. Maybe we will finish today. Okay, so that's the point of the course that we are on the final stretch, and things will start moving very fast here. All right, so let me start my screen share. Okay, so for the next chapter, which is chapter number 9, we will talk about molecular geometry. Okay, so this is a very short chapter, and here it's very important that you have Lewis structures very clear in your mind, because it will be a prereq to be successful here. Okay, so in this chapter, we will basically talk about the Vesper model and polarity of molecules. Unfortunately, we will have to skip valence bond theory and molecular orbital theory due to time constraints. So therefore, just one topic, just the first topic, will be covered in this chapter. Okay, so what's the importance of molecular geometry? Most of the biological processes are based in the interaction between molecules and proteins. In this case, shape and charge distribution play important roles. The recognition between proteins and molecules is strongly dependent on the shape of molecules and proteins. Therefore, having an adequate shape will allow or not the interaction between molecules and proteins. And that's very important in properties, for example, the sweetness of the sugar. Why does sugar have a sweet taste? Okay. What is the part that the molecular geometry plays in the sweet taste of the sugar? And understanding that property allows us to create molecules that trigger the same sensation. If we talk about solubility, CO2 is less soluble in water than SO2. Why? Okay. Both compounds have one central atom and two atoms connected to the central atom. In both cases, we have oxygen connected to the central atom. The only change here is that we are replacing sulfur by carbon, and that changes completely the solubility in water. So the shape of the molecule will play a very important factor in solubility of compounds. And molecular geometry is very important as well in the chemical process behind vision. So with that being said, let's start talking about molecular geometry. Again, keep in mind that you need to know how to draw Lewis structures. Just follow what we have been doing in this week and last week as well. Remember that sometimes you have two or more possibilities for the Lewis structure of a compound. The way to decide between several possibilities is by determining the formal charge of the atoms in the compound. Any compound likes to have formal charges 0 on the atoms that will render stability. Double or triple charges are not stable. And if we cannot have neutral charges in all the atoms, and we need to have a negative charge, for example, the negative charge has to be located at the most electronegative atom. For example, if we look at the nitrate ion, we know using the Clark's rule that we need to have a double bond, one double bond, and therefore two single bonds between the nitrogen and the other two oxygens. When we calculate the formal charge for all the atoms, the N double O atom has formal charge 0. We have here a negative charge located in at the two oxygens and a positive charge located at the nitrogen. Okay. Although all the charges are not 0, we have here the negative charge located at the most electronegative element in this chemical bond. Therefore, this will give us a stable structure. Remember that if you sum all the formal charges from all the atoms in the structure, you have to get the charge of the compound outside here. Okay, so every time you have a charged compound and you are drawing the Lewis structure, put the structure in between parentheses and put the sign of the charge outside here of the parentheses. And that will indicate that the whole compound is charged. Okay, very good. So therefore, Lewis structures only tell us how the electrons are being shared, but not how they are organized in space. For example, for the CO2 molecule, what is the most stable organization in the space for the three atoms that form the molecule? Is it like a linear shape, or is it like a right-angled shape? And that's the goal for this chapter, is to determine which arrangement is the most stable and the one that the molecule will prefer. To do that, we are going to use the Vesper model. In the Vesper model, any system tends to adopt a spatial configuration that decreases the repulsion between the electrons. Therefore, the molecule will arrange all the atoms and non-bonding pairs in a way to minimize the electronic repulsion. Therefore, when electron pairs are separated by 90 degrees, that has a higher repulsion than when they are separated by 120 degrees. and that's higher repulsion than when they are separated by 180 degrees. Okay, so see here, as I move the electrons further apart, the repulsion decreases, and the molecule will adopt the configuration which has the least repulsion between the electrons. So that's the first rule. And now the second rule, the repulsion between two lone pairs is stronger than the repulsion between a lone pair and bonding pair, which is stronger than the repulsion between bonding pair and bonding pair. So every time you have a lone pair in the central atom, usually the repulsion will increase, and that will affect the molecular geometry. And of course, here we are looking at the molecular geometry for the central atom. Okay, so what is the procedure that we are going to follow to determine the molecular geometry for the central atom? First step is to look at the electron pair geometry. The electron pair geometry is going to look first at the central atom and see everything that is around the central atom. Therefore, we will count the covalent bonds and also the lone pairs if they exist around the central atom. Okay, so electron pair geometry is the relative position in the space of all the bonding and non-bonding pairs around the central atom. So that will give us an first look at the geometry. And then after we determined the electron pair geometry, now we can determine the molecular geometry of the compound. Molecular geometry is the relative position of all the bonding pairs around the central atom. Okay, see the difference? Electron pair geometry will take into account bonding and non-bonding pairs, while the molecular geometry will only look at the bonding pairs. Therefore, the step number one is to determine the electron pair geometry. Okay, step 1A. To determine the electron pair geometry, we will first determine the steric number and then organize the bonding and non-bonding pairs around the central atom to minimize the repulsion. So let me switch to my other screen here, then I can write some stuff. Okay, very good. To determine the steric number for the central atom, we are going to consider that a lone pair is a unit, a single bond is a unit, a double bond is a unit, and a triple bond is a unit. And we are going to add everything we have around the central atom. So let me show you here two examples. First one is for the nitrate, and the second one for the water molecule. So first goal here is to determine the steric number, and then we are going to organize everything that's around the atom in the space. So steric number. So let's look always at the central atom. A double bond will contribute to the steric number with an unit, and each single bond will contribute with an unit to the steric number as well. In this case, we don't have any lone pair. Therefore, the steric number for the nitrate ion is going to be 1 plus 1 plus 1, which is 3. And let's do the same thing for the water molecule. And we are going to look at the central atom, which is, in this case, oxygen. And I'm going to do the same thing. Determine the steric number for the oxygen atom. In this case, we have two lone pairs, okay? So each lone pair will contribute with an unit for the steric number. And we also have two single bonds. So therefore, each single bond contributes with an unit for the steric number. Therefore, the total steric number for the oxygen is going to be 1 plus 1 plus 1 plus 1, which is 4. Now that we know the steric number for the first case and the second case, we are going to try to organize the things that are around the central atom in the space in a way to minimize the repulsion.
Excuse me, George.
Yes.
Why did you count the lone pairs on the H2O but not the previous example?
Okay, so we are always looking at the central atom for the molecular geometry. Okay, so see here that the first example for the nitrate, we are looking always at the central atom, which is nitrogen, correct?
Okay, thank you.
See here?
Yes.
Understood?
Yes.
Okay, cool. Yes, whatever is on the oxygens, that will not matter for the molecular geometry. Okay, so now that we know the steric number, let's see what's the best way to organize 3 groups in the space for the nitrate, and what's the best way to organize 4 groups in the space for the water molecule. So let me go back to the PowerPoint for that. Okay, so now that we know how to determine the steric number, I have here a figure with all the possibilities that we may face. So if we have a steric number equals to 2, what's the best way to organize 2 things around the central atom to minimize the repulsion? put them as far as you can, and therefore that's going to be a linear arrangement. If we have three atoms around the central atom, the best way to organize three groups around a central atom is in a trigonal planar geometry. It's like a triangle here. Four groups around the central atom, the best way to organize four groups around the central atom that will minimize the repulsion is in a tetrahedral geometry. Five groups around the central atom. Now look, we have a trigonal by pyramidal geometry. Okay, so a triangle on the plane, and then one group up, and then one group down. When we move on to six groups around the central atom, the best way to organize six groups around a central atom to minimize repulsion is in an octahedral fashion. Okay, we have a square in the plane, one group up, one group down. Steric number 7 is not usual, but it's going to be a pentagonal bipyramidal geometry. So you have a pentagon on the plane, and then one group up, one group down. And this is very rare. Steric number equals to 8. So we are going to have a square anti-prismatic geometry. So you have the central atom here in the middle, and then you have 1, 2, 3, and 4 groups up. So they are coming out of the plane, and then the other 4 groups going into the plane, and they are not aligned between themselves. Okay, for this part here, you have to be good with drawings. Okay, so now that we know how to arrange the groups as a function of the steric number to minimize the repulsion, so let's go back to the example that we are working with. Okay, so we determined the steric number for the nitrate equals 2, 3, and then steric number for the water molecule, specifically the central atom, and we got number 4. So with that, now we are able to tell what is the electron pair geometry for each case. If we have steric number equals to 3, The best way to organize this in the space is in a trigonal planar geometry. So you're going to have something similar to that. Okay, so see here, the middle atom is the nitrogen, and we have three groups around the nitrogen. And we are organizing these three groups as far as we can to minimize the repulsion. Therefore, steric number equal to 3. The electron pair geometry is going to be trigonal planar. What about the electron pair geometry for the oxygen atom in the water molecule? Now we have four groups around the oxygen. The best way to organize four groups in the space in a way to minimize the repulsion is like a tetrahedral. Okay. So, see here. So we have one group up. This group here is moving from the screen towards me. This other group is moving in the opposite direction from the screen farther from me. And then we have another group here. Okay. So four groups. The best way to organize them is in a tetrahedral geometry. Therefore, the electron pair geometry for the oxygen atom in the water molecule is tetrahedral. Okay, that's almost done to get the molecular geometry. Okay, go back to the PowerPoint. Okay, so now finally, to get the molecular geometry, we are going to place the atoms in the available positions. And you can always refer back to this table. So here we have the steric number. So 2, 3, 4, 5, and 6. So remember that the steric number counts bonds, bonding and non-bonding electrons around the central atom. And then on the top of the table is the number of lone pairs located on the central atom. Okay, so if we have a steric number 2 and no lone pairs around the central atom, the molecular geometry then is going to be linear. Let's see the nitrate case. We have steric number equals to 3. No lone pairs around the central atom. Therefore, the molecular geometry is going to be trigonal planar. Okay, so we had determined that the electron pair geometry is trigonal. We have 3 atoms of oxygen around the nitrogen, and the 3 atoms are going to fill up the available positions. Therefore, in this case, the electron pair geometry is going to be the same as the molecular geometry, which is trigonal planar. And let's take a look now at the case of the oxygen in the water molecule. We know that the steric number is 4. And For that case, we have two lone pairs located on the oxygen atom. Okay. So therefore, what we have here is four positions. However, only two positions are occupied by the hydrogen atoms. So all of them are equivalent. So no matter where you place them, that's going to be the same. So what we have here, counting everything, is tetrahedral. For the molecular geometry, you are just going to erase the lone pairs and see what is left. Okay. So therefore, when we are talking about water, we have steric number 4. However, we have two lone pairs located on the central atom. Therefore, we are going to get a bent molecular geometry. Okay, and that's going to look like something like that. Therefore, the biggest difference between electron pair and molecular geometry is that for the first case, you are going to consider bonding and non-bonding pairs that will arrange everything in the space. And for molecular geometry, we are going to look at only the positions occupied by atoms. And that was the case for the water, where the electron pair geometry is tetrahedral. However, the molecular geometry is bent because we are not looking at the two lone pairs at those positions over here. You can always refer back to this table to help you to determine molecular geometry. Okay, so again, this table is useful for determining the molecular geometry, while this figure here is useful to determine the electron pair geometry. Okay, so let's work some examples here. So the goal here is to determine first the electron pair geometry for CO2. On nitrate we already did, and PCl5. Okay, so let's work with CO2 and PCl5 because nitrate was already tackled. So first, of course, draw the Lewis structure, then determine the electron pair geometry, and from there, let's determine the molecular geometry. I'm going to give you a couple minutes to start, and then we will solve together. Okay, so let's start with CO2. So we are not doing nitrate because that was the first example. So starting here with CO2. Oh, sorry. Just forgot here to switch. Okay. Okay, so first step is to draw the Lewis structure. And again, I'm going to tell this again. This is a course that you cannot compartmentalize the information. Everything you have learned, it's somehow going to be used again. Okay, so CO2, let's tackle here really quick. According to Clark's rule, you have two double bonds or one triple bond and one single bond. We already did this example, and the most stable structure is the one that has two double bonds around the carbon atom, and we are going to fill up the octet shell, the octet for the oxygen atoms with the leftover electrons. And again, for the geometry, we're going to look at the central atom. First step here is to determine the steric number. The steric number is going to look at bonding and non-bonding electrons around the central atom. Single bond count as 1, double bond as 1, triple bond as 1, and lone pairs as 1 as well. So around the carbon atom, we have one double bond and another double bond. Therefore, the steric number for carbon is going to be 1 plus 1, which is 2. The steric number will tell us the electron pair geometry. When you have steric number 2, the only possible electron pair geometry to minimize the repulsion is linear. So therefore, the two groups around the carbon atom are arranged in a linear geometry. So we have here the central atom and then the two groups around the central atom. Okay, so now let's look at the molecular geometry. For the molecular geometry, you can look at that big table that I showed you, and I'm showing part of the table on the right side here. So in this case, we have steric number 2 and no lone pairs around the central atom. Therefore, in this case, the molecular geometry for CO2 is also going to be linear. That means the two available positions around the carbon atom are occupied by the two oxygens. And therefore, this is how the CO2 molecule is arranged in the space. And that's why we draw CO2 as a linear molecule and not as a right-angled molecule. Okay, so this one is the most stable configuration for the CO2 molecule. Okay, so now let's work with the second example, PCl5. Okay, so let's build the Lewis structure of PCl5. For this step, it doesn't matter how we organize the bonds in the space. So according to the Clark's rule, PCl5 is an example of octet expansion for the central atom. So we are going to have phosphorus in the middle, surrounded by 5 atoms of chlorine, and the leftover electrons are going to be used to fill up the octet of the chlorine atoms. Okay, so now that we know the Lewis structure for the compound, first step towards the determination of the electron pair and the molecular geometry is the determination of the steric number around the central atom. Okay, so always looking around the central atom. Each single bond contributes with 1 unit to the steric number. So 1 plus 1 plus 1 plus 1 plus 1. Therefore, we are going to get a steric number equals to 5. So we have 5 groups around the phosphorus. What is the best way to organize 5 groups around an atom? So go back to that first slide that I showed you with the geometries as a function of the steric number. The easiest and most stable way to organize 5 groups around a central atom is as a trigonal bipyramid. And that's going to yield something like that. Okay, so now here we are counting bonding and non-bonding electrons if they exist. So with the electron pair geometry, now let's determine the molecular geometry. For the molecular geometry, you can use that big table that I showed you. In this case, we have steric number 5, no lone pairs around the central atom. Therefore, the molecular geometry in this case is going to be the same as the electron pair geometry, trigonal by pyramid. Okay, so we had 5 positions available, and all the 5 positions are occupied by chlorine atoms. And that's going to be the molecular geometry. Okay, so see here in the drawing for the trigonal bipyramids that one of the bonds are in bold. So that means that this bond is going out of the plane. So it's this one over here. And there is another one like a dashed bond. So that means the bond is going deeper in the plane. So going backwards, kind of. So that's this bond over here. So using bold and dash is a way to represent that the bond is going out of the plane or towards the plane. Okay, so with that, we are going to stop here today. So next week, we will talk about the polarity of the molecules. Have a good weekend.
Thanks, George, you too.
Bye.
Bye-bye.
Thank you.
Thanks, Professor.
Thank
Do
you.
you
Have a nice
mind-
day.
Could you possibly scroll up one more slide
Yes.
with the CO2 example?
CO2, yep.
Yes,
right
I just
there.
wanted to take a screenshot just so I could transcribe it.
No problem.
Perfect. Thank you very much, Professor. Have a great weekend.
You too. Bye-bye.
Hey, Professor, sorry for bothering. I was wondering if I can get an extension for homework 7.
Yes. Do you need tonight, tomorrow,
Sunday?
Sunday?
Yeah.
Yes.
All right.
Sunday. What time?
Until midnight?
Yep.
Okay.
I will extend it.
All right. Thank you, Professor.
Yep. Bye-bye. Have
a
a
good
good
day.
weekend.